Hi, welcome back. So today, again, last time, we finished discrete time signal spaces, and we started talking about continuous time signal spaces. And in that initial discussion, we came up with some questions that we wanted to answer. Two of the elementary ones we answered, and the remaining two had to do with the sort of norm structure of spaces of continuous signals. And so remember, we decided that every space of continuous time signals on a continuous time domain T should contain those continuous signals with compact support. Okay, and I sort of chatted through a process by which we rationalized this choice. Okay. And the questions that we want to think about now amount to the structure of the normed vector space. Consisting of these continuous signals of compact support. With the various p norms. Okay, and there's lots of things you can say about the structure of these. I'm interested mainly in their completeness. Okay. So for a given time domain and for a given p, is the space complete? Okay, and if it's not complete, what's its completion? All right, so that's what I'm interested in. And we're first going to look at the case where p is equal to infinity. So we're going to look at continuous time signal spaces with the infinity norm. Okay. All right. So so we're going to let T be a continuous time domain. Okay, and let F, as always, be R or C. Okay, and remember that the infinity norm is the sup of the modulus or absolute value of F over the time domain T. Okay, and when F is in this space C0 CBT, this is less than infinity. Okay, so we showed that last time. All right. Okay, so let's first think about what convergence in the infinity norm is. Okay, and to answer that question, I'm going to recall, I sort of assume you've seen these concepts before, but I'm going to make the definitions in any case about pointwise and uniform convergence. And I'll make the definitions because we're going to think about these definitions a little bit. So a sequence fj of functions, and these don't have to have necessarily any particular properties. Okay. In particular, I'm not restricting this definition to continuous signals with compact support. They can be arbitrary. Okay, so a sequence of functions fj like so converges. Oh, sorry. All right, so I'm going to give both these definitions at once. So let me try to structure the grammar properly. Converges pointwise to some other function if for every epsilon in positive and t in t, okay, there exists an n such that f at t is within epsilon of fj at t for all sufficiently large j. Okay, so that's pointwise convergence. And let me write down the definition of uniform convergence, and then we'll discuss. So the sequence converges uniformly to f if for every epsilon positive there exists again a sufficiently large integer n such that, and again we require that f of fj of t be within epsilon of f of t for all sufficiently large j's, and now we require this to be true for every t. Okay, so that's pointwise and uniform convergence, and you'll remember that the difference between these two definitions, sort of in terms of the mathematical grammar, is the place in which you locate the t in t. Okay, so in the pointwise convergence definition, you first choose an epsilon and a t. Okay, so now t is fixed, and for that epsilon and for that t, then you find n, and sometimes people will indicate that by putting a subscript on n to denote that it depends on epsilon and t, and that's okay. All right, and then at that t, okay, fj at t is within epsilon of f of t. All right, and the way you should think about this, therefore, is that you fix this t, and then basically what you're doing is you're looking at convergence of the sequence of numbers fj of t to the number f of t. Okay, and then you fix a t and look at convergence of that sequence of numbers to the number f of t. And then if you require that for every t, that's pointwise convergence. Okay. Uniform convergence means that you choose an epsilon, okay, and then you require that this hold with that value of epsilon for not just every sufficiently large j, but also at every t. Okay, and so the uniformity here is you say that this is uniform in t. Okay. In the sense that the number n that you choose here is independent of t. Okay, and again, sometimes people will denote that by putting n sub epsilon there to explicitly denote that n depends on epsilon, but not on t. All right. And a pointwise convergence and uniform convergence are different. The definitions don't the definitions look differently. And certainly it's true that uniform convergence implies pointwise convergence. That's true. Okay. But is it true that pointwise convergence implies uniform convergence? Well, it's not immediately clear from the definition that that's true or false. It's false. And let's see some examples of, see an example of why. Okay, and I'm just going to draw the example. I'm not going to write down the functions because you would only understand it by me drawing it anyway. Okay, so I'm going to consider a sequence of functions defined on the interval 0, 1. Okay. And the functions are going to be, they're going to look like this. Okay, so the first function is going to, so here's going to be the value 1. Okay, so the first function is going to rise to 1 between 0.5 and then sink down to 0 between 0.5 and 0. Okay, and then the next one, it doesn't really matter how you do this, but let's say we choose a third. Okay, and then the next sequence, term in the sequence is going to, all right, so this one rises up like so, and this one rises up like so. And so then, 2/3 is going to be out here somewhere. And so it goes like this. Okay, and then a quarter. All right, so this one is going to rise like so, and then sink like so. Okay, so this is F1, F2, F3. Okay, and so these are like tent functions, and the peak of the tent happens at and the only thing that's really important here is that the peak of the tent happens at a sequence of points that converges to 0. Okay, and here I've explicitly chosen the sequence to be 1/2, 1/3, 1/4, and I guess the next one would be 1/5, and so on. All right. Okay, so we claim here that this sequence Fj converges pointwise, but not uniformly, to the 0 function. Okay, and so again, I'm going to just sort of chat my way through that. So first, let's make sure we understand why it converges pointwise to the 0 function. Okay, so the definition of pointwise convergence says that I choose an epsilon and I choose a t. Okay, and so I'm claiming that I'm converging to 0. Okay, so I'm going to choose, and I don't want to clutter my graph, so I'm just going to kind of throw down points here temporarily with my flashy red marker. Okay, so I choose a t, let's say here. Okay, And what I have to do is, with that t fixed, I have to show that for every epsilon, there exists a capital N, so that fj of t is within epsilon of f of t. Okay, so my point t again is here, and all I need to do to make that work is I need to choose j large enough, and so capital N, so that the peak of my tent, or maybe the left bottom part of my tent is to the left of my point t. And then as long as I do that, then fj at t for j larger than n is going to be identically 0. And so certainly this quantity will be less than epsilon, no matter how small you choose epsilon. Okay. So that gives me pointwise convergence. Okay, but now let me see why it doesn't converge uniformly. Okay, and the way to think about this is you need for this to hold at every t, and so I have a pointwise limit of the sequence of functions, and that's the function f of t equals 0. And so if it converges uniformly, then it has to converge uniformly to 0 because it converges pointwise to 0. And this condition means that I should be able to sort of take a little tube of radius epsilon around the graph of the limit function across the entire domain. And then it must be the case that's what this definition says. It must be the case that f minus fj, the graph of f minus fj should sit inside that tube. But in this case, the limit function is 0, and so the tube is a very simple looking tube. It's that, okay, just a little band about 0 of with 2 epsilon. Okay, so there's my tube, and then f is equal to 0. And so really what I'm asking then is I'm asking that the graph of fj should sit inside that tube for some sufficiently large j. Okay, but I can just see by looking at the graphs of these functions that no matter how large I choose j, the graphs are going to come outside the tube. Okay, and that's why this doesn't converge uniformly. So uniform convergence, again, it means uniform across the domain of the function. Okay. All right. And so the point so again, I expect that you've seen the notions of pointwise and uniform convergence before. And the reason I wanted to spend some time talking about them is because when you think about them for a second, you can see immediately that the following thing is true. So a sequence fj converges uniformly to f, okay, if and only if the limit as j goes to infinity of f minus fj in the infinity norm is equal to 0. Okay. So the point is that uniform convergence is equivalent to convergence in the infinity norm. Okay. All right, and again, that's just because what this is saying is that the graph of the difference function should be contained, right? So the soup of the values of this function should be possible to choose those arbitrarily small, and that statement holds both for this limit being 0 and for uniform convergence. That's so the point is that the proof is sort of more or less obvious from our considerations of this example even. Okay. All right. And let me summarize that discussion with this. Okay. All right. And so in particular, what we know from this discussion is that with the infinity norm, convergent sequences here are exactly uniformly convergent sequences, okay? And so what we want to then understand is that completeness then means that if you take a sequence of continuous signals with compact support, they should converge uniformly to a continuous signal with compact support, okay? And if it's not the case, then we need to talk about completions, all right? So let's look at a case where we do have completeness, okay? And we're going to do that by introducing a new space, which is kind of bigger than the space of continuous signals with compact support, but it has the property of being complete, and then it'll give us kind of a starting point. Okay, so we're going to denote C0 BDD of TF. Okay, and BDD, of course, is going to be bounded. Okay, so these are going to be Fs, which are continuous, of course, with the property that their infinity norm is finite. Okay, because that's exactly what bounded means, of course. It means that the infinity norm is finite. Okay, and so I'm going to claim, so this is maybe sufficiently interesting for me to formalize this a bit. That this space of bounded continuous functions on the time domain T with the infinity norm is a Banach space. Okay, by which, of course, I mean a complete normed vector space. Okay. All right, so what I need to do then is I need to show that every Cauchy sequence in here converges. And so I have to take a Cauchy sequence, show that the limit is both continuous and bounded, right? That's what I need to do. So I'm going to take a Cauchy sequence, Fj. With respect to the infinity norm, of course. Okay. So I'm assuming you've seen arguments like this in your analysis course when you talked about uniform convergence, and you probably had some result like a uniform limit of continuous functions is continuous, which is true in some setup. Okay, here I'm proving it for bounded signals. Okay. All right, so the first thing I'm going to claim is that the sequence converges pointwise. Okay, to something. I don't know what it is. All I know is it converges pointwise. And so by the definition of pointwise convergence, I choose an epsilon and a t. Okay, and because this sequence is a Cauchy sequence in the infinity norm, okay, I know that I can let epsilon, n be such that fj minus fk in the infinity norm is less than epsilon for j and k larger than n. Okay. So in particular, okay, because by the infinity norm, this means the soup of this thing evaluated, the soup across T of this thing evaluated at all T's, okay? And so in particular, at the T that I've chosen, Fj of T minus Fk of T must be less than epsilon in absolute value. Okay, so thus this shows then that this sequence of numbers okay, because I'm evaluating at T. It shows that this sequence of numbers is a Cauchy sequence. In F. Okay. Right, because that's exactly what I have, right? It's just that means exactly that it's a Cauchy sequence. Completeness of F gives convergence and we denote the limit so f of t is the limit as j goes to infinity fj of t. Okay. All right, so this is what you call the pointwise limit. Okay. And we don't know anything about it really at this point. All we know is that it exists. So at every t, there is such a number, which is the limit of the sequence, and I denote that number by f of t. Okay, the next thing I'm going to show is that the sequence fj converges uniformly, okay, and therefore in the infinity norm. Okay, just by this statement that I made here. Okay. It converges uniformly to F, okay, where F is this thing that I defined above. All right. Okay, so I always find it both illustrative and easier to kind of work this out as I go along rather than presenting it as if I knew what I was doing in the first place. And I mean by that, what do I need to show? Okay, so what I need to show is I need to show that f of t minus fj of t is small for every t, okay, and for every large enough j, okay. And so what do I know? I know that at a fixed t, okay, I know that given a j, sorry, at a fixed t, I can find an n so that this is true for all sufficiently large n. Okay, so I'm going to, kind of want to make use of that fact. So what I'm going to do is I'm going to just do this. I'm going to just throw in some F, and I need to think about what Fk has to be. Okay. All right. Okay. So now I've sort of seen what it is that I need to try to do. I need to try to make this thing small, and I need to make this thing small. And I know that I can make this thing small by choosing K large enough and I know that because I have pointwise convergence. Okay, and I also know that I can make this thing small because the sequence is Cauchy. Okay, and this thing can be made small uniformly in T. Okay, all right. So therefore, what I do is the following thing: I let room here. I let epsilon and be positive, and T be in the time domain. Okay, and I need to find an N large enough so that both of these terms become small. Okay, for large enough J. Okay, now so I'm not going to have enough room to say this, so I apologize. I should have moved. I should have. In fact, I can do that, can't I? So let me do that. Let me just move. Sorry. Well, let me do that, I guess. All right. So there. Okay. Okay, good. So I'm going to take an epsilon and a T. And again, what I need to do is I need to find an N large enough so that if J is larger than N, then this thing is small. And I'm going to do that by making each of these small. Okay. All right, good. So sorry about the space issues. Okay, so first, let N1 be such that, okay, now here, I'm going to work with a fixed T, and I'm going to use pointwise convergence, okay? Let N1 be such that F of T minus F K of T is less than epsilon over 2 for K greater than or equal to N1, okay? All right, and I know I can do this by pointwise convergence of the sequence, okay? Now, let N2 be such that Fj of T minus Fk of T is less than epsilon over 2, okay, for J and K greater than or equal to N2, and because the sequence is a Cauchy sequence in the infinity norm, I can require that this be less than or equal to epsilon over 2 for every T. Okay. All right. So now, so K here is kind of we kind of wash K away. Okay. Sorry, K. Sorry. All right. So we wash K away here and here. The only thing we're really interested in is J. Okay. So now we let J be greater than or equal to N2. All right. So N2 now doesn't depend on T, right? Because I'm using the uniformly Cauchy condition here. All right. N1, however, does depend on T. Okay, because N1 is using pointwise convergence. And so this N1 will depend on T. And so I need to choose K large enough so that both of these conditions are satisfied. Okay, so I'm going to let J be greater than or equal to N2 and K to be greater than or equal to the max of N1 and N2. Okay, so then, I have this calculation. Okay, and so this is true then for all J's greater than or equal to N2. Okay, and the fact that, you know, this N1 here that I've chosen depends on T, it kind of doesn't matter because it gets washed out in this sort of plussing and minusing here. And so the point is that this is less than epsilon, okay, for every J greater than or equal to N2. Right. So this is an argument that requires a bit of looking at before you believe that it's correct. And it's exactly because, you know, somehow you feel like this is dishonest because N1 depends on T, and you need for this to be true for every T. Okay. But the point is, this is true for every J greater than or equal to N2, and N2 does not depend on T. Okay. All right, good. All right, so I've shown that the sequence converges uniformly, and as we said before, that means convergence in the infinity norm. Okay. Now I'm going to show that the limit f, the pointwise limit, is bounded. Okay, f is bounded. All right, and so again, you know, it's worth just sort of writing down, I need for this to be bounded uniformly in T. Okay, and so the way I'm going to do this is I'm going to, you know, again, just add and subtract stuff. Okay, so this is going to be f of T plus, sorry, minus fj of T, okay, plus fj of T by the triangle inequality. Okay, so I just added and subtracted fj. All right, so now above, I just showed that fj converges uniformly to f. Okay, and so I know that by choosing j large enough, I can ensure that this thing is, you know, actually I can ensure that it's as small as I want. And so in particular, I can ensure that it's less than 1. Okay, all right, so now let n be in the positive integers such that f of T minus fj of T is less than 1, and this is true for every j greater than or equal to n, and T in T. Then, okay, and so the point is, you know, I can just choose a specific j, and I'm going to choose n. All right, and so this is less than or equal to 1 plus the infinity norm of fn. Okay, and this is right, this is finite, and so what I've done is for every t, I've bounded this thing by some constant which is independent of t. Okay, so this is true for every t time domain. Okay, so that's boundedness of the pointwise limit. And so the only thing then that remains is to show that the pointwise limit is continuous. All right. All right. Okay, so again, let me just kind of write down what it is that I need to be small and then think about, adding and subtracting things, right? So what I need to be small for continuity is I need I choose a T naught, right? And I need to show that for T close enough to T naught, this thing can be made small. All right. And so what I'm going to do, by adding and subtracting things, you hope to decompose this into, a sum of things by the triangle inequality, each of which can be made small. All right. And so by the triangle inequality, here's how I'm going to do this. All right. So I go f of t minus f, let's say j of t, and we have to think about what j should be. Okay. And I know that I like this because this can be made small by uniform convergence of fj to f. Okay, so then I need to, I've subtracted fj, so I need to add fj. Okay. And now I need to think about something that is close to fj, and it's not f of t naught, right? F of t naught, there's no reason for that to be close to fj of t, but certainly fj is continuous, and so I know that fj of t naught will be close to to fj of t, so I can do this. Okay, and then so I've now added or I've subtracted fj of t naught, so I need to add it, and I'm going to sort of change the order by the absolute value to write that like this. Okay, so just by adding and subtracting, first fj of t and then fj of t naught, I end up with three terms, and it seems like I should be able to make these small, right? This is small by uniform convergence, this is small by continuity of fj, and this is small by uniform convergence. All right. So let n be an integer. I apologize. So before I did any of this, I apparently chose some epsilon. Okay, right there. Okay, so I take some positive epsilon, and then given that epsilon, I choose n, so that this thing is less than epsilon for j greater than or equal to n, and for t in the top domain. Okay, that's by uniform convergence, which I proved in step 2. All right, and now by continuity of, and so here I'm going to do rather like I did up here, and I'm going to choose j to be equal to n. I can do that easily enough. So let me do that. Sorry, I'm just going to kill. All right, so I'm going to use fn here. So that's the specific j that I'm going to choose. Okay. All right, so I'm sort of showing you the kind of the guts of this argument. All right, so now I'm going to let delta by continuity of fn be positive. Be such that f of t, fn of t minus fn of t naught is less than, oh, and sorry, I need epsilon over 3 there. And similarly, epsilon over 3 for t within delta t naught. Okay, good. All right, so then finally, for okay, so now I can go to the calculations that I kind of sketched in the beginning. Okay, so I'm going to take t to be within delta of t naught. Okay, because this is the thing that I'm interested in making small. Okay, so now I know that this thing by this condition is going to be less than epsilon over 3. This by this condition is going to be less than epsilon over 3. And then this, again, by the uniform convergence condition, is going to be less than epsilon over 3. So this is all less than epsilon. All right, and that does it. Okay, so I've shown that that if I have a Cauchy sequence, okay, in the infinity norm, in the space of continuous bounded signals on a time domain, then I prove pointwise convergence first, just so I could have something to talk about, F, all right? Then I prove uniform convergence. Then I prove boundedness. And then I prove continuity, all right? So every Cauchy sequence in here converges to a pointwise to a limit, and moreover converges uniformly to a limit function which is continuous and bounded. And that's all I need to do to show that that's a Banach space. Okay, good. All right, so the space and so let me sort of emphasize this. The Banach space C0 bounded is the continuous time analog time analog. There's maybe another one that's an analog too, and we'll talk about it. There's also a space called big L infinity. Okay, but for our purposes right now, we can think of this as being analogous to little L infinity, right? Okay. So notice that if T is compact, then we have the following inclusions. We have C0, CPT, not inclusions, equalities, is equal to C0 bounded is equal to C0. Okay. Now, why are these true? Well, certainly you have an inclusion like this, okay, in all cases, all right? And so what you really need to show then is that a continuous signal on a compact time domain has compact support, okay? So to prove this, Note that, sorry, let me say it this way. Let F be in C0. Okay. What we need to do is we need to show that it's necessarily the case that F has compact support. Okay. Then, what's the support of F? Okay, well, the definition that I gave is that you take the set of points, T, so that F of T is not 0. Okay, then you take its closure. Okay, and then you intersect it with T. Okay, now, so we're taking the closure now of a set of points in T. All right, T is already closed, right? So it's compact, meaning in this case it's closed and bounded. All right. Remain inside T. Okay. So therefore, the thing that we observe is that this closure is already contained in T. Okay, and this is since T is closed. Okay, so if you have a closed set and you take the closure of a subset which is contained in there, then you know, the closure is still contained in the closed set. All right. And so that means, therefore, that this intersection here is unnecessary. Okay, so this is the closure of T in T. Okay, and so this implies that the support of F is a closed, remember this closure here is being taken in R. Okay, not necessarily in T, right? But the closure is the closure of this subset as a subset of R. Okay, and so what this shows is that the support of F is, because it's the closure of something, is a closed subset of T. Okay. Now, because closed subsets of compact sets are compact, okay. All right, so that's something you learned in your analysis course. Okay, and so therefore, I've shown that F is in C0 CPT. Okay, and so I have these inclusions, obviously, and then I have that, oopsie. I have that inclusion as well. All right. Okay, good. And so in particular, if T is compact, then C0 CPT T is complete. Okay, and then you in the case when the time domain is compact, this is just C0. Okay, so when T is compact, you don't really ever think about C0 CPT. You just think about C0. Okay, because those things are the same. Okay, but remember that our objective here is to think about starting with this space and asking when is it complete in the infinity norm. Okay, and so for the purposes of that question, this is the space you want to talk about, and when T is compact, this is complete. Okay, and in fact, so that's the only situation where this space with the infinity norm is complete. Okay, and maybe what I'll do is finish that part of the discussion next time.